So we'll continue our foray into modern abstract algebra. And remember, the idea here is that we really just want to kind of pinpoint how to generally describe operations between sets, algebraic operations between sets. And the whole idea here is to really focus on examples that are related to the mathematical objects under consideration in this course. Specifically, we've been really looking at the set of modular integers, mod m. So, on this topic, then the next type of mathematical algebraic structure that we have to define is called a ring. A ring is a set A equipped with two binary operations. Or functions from A cross A back into A. And we can denote these two operations as star plus and star dot. And the reason behind this notation is that plus is very similar to addition operation, has the same properties as an addition operation, and the star dot has similar properties to the multiplication operation. However, the idea here is these are completely different operations, and they're general operations defined on the set A that there will be many specific examples of as we kind of move along. And so we assume these two operations must satisfy the following axioms. Axiom 1 is that A, comma, operation plus must be an abelian group, meaning that for any element in A, there must be an additive inverse, or an inverse with respect to this star plus operation. This star plus operation must be associative, and there must be an identity element in the set A with respect to this star plus operation. More so, it must be commutative with respect to this plus operation. So, hence the abelian group assumption. In general, typically we denote E as the identity element. For this abelian group. The second axiom is that the set A with the binary dot operation, which is analogous to multiplication, is a monoid, or it has to be associative, and there has to exist an identity element with respect to this dot operation, star dot. And 3 that the star dot operation must be both left and right distributive with respect to the addition operation. And we've already talked about what 1 and 2 mean because we've defined both abelian group and monoid, but I'll write down what this means. For any A, B, C in the set A, we have to have that A star dot B star plus C is going to be equal to A star dot B star plus A star dot C. This is left distributivity. And right distributivity is going to be that B star plus C star dot C star dot A has to be equal to A star dot B star dot A star plus C star dot A. And this is important to distinguish between left and right distributivity because in general, right, A comma star dot is only a monoid, which means it's non-commutative in general. If we have commutativity with respect to this star dot operation, then this is going to become a commutative ring. In which case, left and right distributivity are the same statement. Notationally speaking, the ring can be written as the set A, comma, star plus, star dot, and we use this to write down the set that the ring is defined on, the plus operation, and the multiplication operation defined on that ring. So let's go over a number of different examples. So we have that set Z, comma, normal integer addition, and normal integer multiplication is a ring. I'll say the following are all rings. The set of rational numbers with normal rational number addition and multiplication is a ring. A set of real numbers with normal real number addition and multiplication is a ring. And lastly, the set of all complex numbers with normal complex addition and complex multiplication is a ring. And some of these are actually, or can be made into even stronger set, so a more complicated set called a field. But in general, all of these sets satisfy the properties of rings, and therefore they're all rings. A Boolean ring is a ring for which any element x in the set A satisfies x squared, which is going to be x star dot x is equal to itself. So for one example of a Boolean ring, consider the set z mod 2z, set of integers modulo 2, which is two equivalence classes, the equivalence class of 0 and the equivalence class of 1. We know this is a set theoretically isomorphic to the set 0, 1, which is z2, and we sometimes call this a Boolean set because it's a set with just a 0 value and a 1 value in it. And for any two A, B in this set, we define A plus B to be A plus B mod 2. We define A times B to be A times B mod 2. This is a Boolean ring because for all of the elements in the set, A or B, these operations definitely satisfy the properties of a ring, which you should go through and verify. But if we go through and look at A can be 1, B can be 1, A can be 1, B can be 0, A could be 0, B could be 1, and A could be 0, B could be 0. So we can actually list out all of the possible values that these mappings give in this ring. And sure enough, A star plus B when A is 1 and B is 1 is going to be 0. It's going to be 1 when A is 1, B is 0, 1 when A is 0, B is 1, and then 0 when A is 0 and B is 0. And A times B is going to be 1 when A is 1 and B is 1, and it's going to be 0 for all of their values. And so what's interesting here is if you consider, we'll consider both elements. We can do this for both elements. The 1 squared is going to be 1 star dot 1, which is 1 times 1 mod 2, which would just be 1. And similarly, 0 squared is going to be equal to 0 star dot 0, which is 0 times 0 mod 2, which is equal to 0. So this is why this is an example of a Boolean ring. And what's also interesting is you want to see here that for the addition operation in the Boolean ring, we're getting what looks very similar to and is actually the same thing as the exclusive OR operation, or in terms of sets, the symmetric difference and for the multiplication operation in the this example of a Boolean ring, we're getting the AND operation or in terms of sets, the intersection operation. And what's interesting here then is that we can actually define a much more general Boolean ring in terms of these set operations. So this is going to be example 2 of a Boolean ring. Suppose that S is a set and the power set of S is the set that we're considering this ring on, and for A and B in the power set of S, the subsets of S, we define A star plus B to be the symmetric difference between the two sets. Which I gave 2 notations for previously. This is just the set A minus B union the set B minus A. And likewise we define the multiplication operation to be the intersection. Sure enough, this is going to be a Boolean ring because for any set C, it's a subset of S, so in the power set of S, C squared, or C star dot itself, is just going to be C intersected with C, which is equal to itself. So for any set, we have a Boolean ring, which is it's a pretty neat example, and it shows a very, very close relationship between rings and fundamental logic, and then also rings and basic set theory. And all of the previous examples are commutative rings. Meaning the multiplication or order of operation doesn't matter. You'll get the same element regardless of the order. And even it's a little bit more difficult to show, but a general Boolean ring is also a commutative ring. This is a property that we can prove. And it's relatively easy to do so. But I wanted to add one more very important definition of a ring. Based on what we're studying right now, and this is that of ZM with modular addition and modular multiplication, mod M. ZM plus M abelian group. Because addition is associative, commutative. There exists an identity element, namely 0, and there always exists an inverse, or a number that you can add to get to a number that's congruent to m. So therefore, this is an abelian group. Z mod m in modular multiplication is a monoid, meaning that there exists a identity element, namely 1, that for any two integers you can multiply them, or any integer by 1, and it'll be congruent to itself. And this multiplication, modular multiplication, is associative. And lastly, we have distributivity. Modular multiplication is both left and right distributive over modular addition. And we can even make the previous a little bit more precise. This is a commutative monoid, because the order of modular multiplication doesn't matter. You multiply a times b, it's the same as b times a mod m. So this is a commutative ring. For one more really important commutative ring, you can actually consider the set of general polynomials with coefficients that are in the ring. So this is actually given a ring. So for any ring R, the set of finite polynomials on some symbol x. We'll use capital X here. Is a commutative ring. And I want to be specific here. If A is an element in the set R of X, then A is expressible as a summation k equals 0 to n of a k, where all of these AKs are elements of the set A that the ring R is defined on, times x to the k, or a naught times x to the power 0 plus a naught times x to the power 1 plus a1 times x to the power 2 all the way up to an times x to the power n. Now I want to be very, very clear here. The addition and the variable, I shouldn't even say variable, and the placeholder x and the powers, again I'm going to put quotations here, the powers of x are simply notational placeholders. Meaning we're not talking about a polynomial function where we plug in some value of x. These things are just symbols that are sort of holding the place of each one of the elements of the ring, and we're using operations or like the rules of operations for normal polynomials to manipulate elements of this ring. Certainly for if our coefficients are coming from, say, the real numbers or the complex numbers, then we can talk about these things as functions. We can kind of show that some very interesting things relating it to functions with coefficients in, say, the real numbers. But for a general ring, this is just a notational convenience, right, to be understood like that. And what we say then is that for two polynomials, a and b, a star plus b, the ring operation is going to be a naught star plus b naught and plus a1 star plus b1 x plus all the way up to an star plus bn, which has a simpler expression in terms of standard summation notation. This is just the sum up to n of a naught star plus ak star plus bk times x to the power times x to the k. Likewise, we can go through and define multiplication on this ring to be completely analogous to normal multiplication of polynomials. So this will end up being a naught star dot b naught plus a1 star dot b naught star plus a naught star dot b1 times x plus a2 star dot b1 or b naught star plus a1 star dot b1 star plus a naught star dot b2 times x with the 2 above it. And we continue this process all the way up to, and this can be very nicely represented as the summation from k equals 0 to q of s k x to k, where sk is just A not BK plus A1 BK minus 1. Oh, and this should be a star clause, because we're dealing with general ring elements. A2 BK minus 2 all the way to the final value in SK, which is A K B0. And I also want to make a note here. The endings of each one of these sums is, oops, and I forgot to change this right here too. The endings of both of these sums are going to depend heavily on the number of terms in each one of them. So the ring addition of these two polynomials A and B is if B is a ring polynomial up to some m, then this maximum value in this sum is just going to be B is the maximum value of the degree of A and the degree of B. Just the maximum value of M and N. And likewise, the value Q here, the maximum value in the product sum, when you take the product of two polynomials and distribute, will end up being Q is equal to M plus N, just like for normal polynomials. But this is a very interesting object, and it's an object that you may not have seen or known about. But the idea here is that you can consider for any ring this set, which is quite a set of objects, which is very, very amazing. Because the idea here is that we can get very interesting results for factoring polynomials directly from this idea, and we'll see that for the most common ring that we're going to be using in this class, which is the set of integers, the idea here is that we have in the integers this idea of a division algorithm. We also, for polynomials, have a very nice algorithm for dividing polynomials, right? And this is effectively, in some sense, the same idea as the division algorithm, but for polynomials. And this is directly coming from this idea, which is very cool. And it's also super important in many areas of mathematics. And I just wanted to point out here that this A naught B next to BK, this means A naught star dot BK, so just the ring multiplication operation between the two elements. And I didn't write that in to each one of these because I wanted to save some space here, but just in case you were a little bit confused as to what that element was. So the next example I want to go over is a non-commutative ring, and this is kind of along the same idea as the previous example, which is if we have a ring, or any ring R be set of n by n matrices with entries from R forms a ring with respect to matrix addition, component-wise matrix addition. And this is with respect to the star plus operation and matrix multiplication done with respect to or using the star operation. So A plus B, the ijth component of this is just going to be aij, whatever that element is, which is an element from the ring R, star plus B, and A times B is going to be A I1 star dot B1J plus AI2 star dot Bij or B2J. Oh, and this should be star plus as we're dealing with the general ring operation. Star plus all the way up to star plus A I N star dot B N I N J. So this star plus here is coming from the ring R, and this star dot is coming from the ring R. The operations for the matrix ring are the standard matrix operations. But what's really cool here is that this means that right, we can again construct non-commutative rings, just like before with groups. And you can do it using any normal ring R. So if you want to consider, say, the matrix of polynomials and study that set, sure enough, you can go through and do that. If you want to consider the matrix from a given of elements from a given Boolean ring, you can go through and consider that. And a lot of these things are very interesting and useful in applications, because this is how we go through and show that certain objects, mathematical objects, are directly the same as one another. And if I can say prove something about one mathematical object, like a general ring, it has to apply to all rings, which is the main thing that's really important about this abstract algebra. Same thing with group. If I can prove something about groups in general, then it has to apply to all groups. So what I want to do is give you a non-example of a ring, and right, you might be thinking of some non-examples already. But if we again take the Boolean domain, Z2, and we define the operations to be star plus is A or B and star times is A and B, and this is not a ring. And you might think, oh well, why is this not a ring? Well, the main reason here is that the set B comma star plus, this must be in a abelian group. And so let's check and see if this is an abelian group. This is, for this Boolean set, the star plus is the OR operation on bits 0 and 1, and star times is the AND operation. So an abelian group means that first we must have commutativity, and we know that A or B or C is going to always, for the inputs 0 and 1, give us that the same thing as A or B or C. So it is commutative, or it is associative here. We have an identity element, 0 or A is equal to A or 0, which is equal to A itself. So we have associativity, and we have identity, the existence of an identity element, namely 0. We also have commutativity. For any two elements in the set, A or B is equal to B or A. But what we're lacking is the existence of an inverse, right? Because we have only one element that we have to look for an inverse of. It's this element 1, and 1 or A for both 1 and for 0 will always be equal to 1. Therefore, there is no inverse in this set. Therefore, this is not a ring. But it is associative, it has identity element, and it is commutative. So it is what's called a commutative monoid, or commutative monoid. And it's also relatively straightforward to go through and show that B comma star plus is a monoid, even that it's a commutative monoid, because A and B equals B and A. And it's also straightforward to go through and show that it's distributive. Oh, sorry, this is B comma the multiplication operation, or the AND operation here. And so when the set under, and here I wrote B, but I'm just using that for Z2, so I don't have to write Z2 every single time. So when you have a set that the addition operation ends up failing to have an inverse, right? And the set under the addition operation is a commutative monoid, or just a monoid in general. We call this a semi-ring. Notice it satisfies all the properties of a ring except for the fact that there's no inverse with respect to the addition element. So we see that b comma star plus star dot is a commutative semi-ring. And this is a very important commutative semi-ring, especially with respect to the previous idea of creating matrices from rings, because this is directly the ring. Its ring is directly related to the Boolean product matrices that we talked about before. Specifically using our notation Mn that we introduced earlier, Mn of this B, this Boolean set of 0, 1, is the set of all n by n matrices from, or with elements from B, or with elements that are 0 and 1. And it's relatively easy to show that this set, which I'll call M for short, M comma star plus or M comma addition and the product of the Boolean product that we defined before is a non-commutative semi-ring. Because the Boolean product A times B is not in general the same thing as the Boolean product B times A. And we already know why this is, but just for an example, consider this matrix, Boolean product with this matrix right here. The output is this matrix, and this matrix, Boolean product with this matrix, which is just the reverse of these two. So if this is A, and this is B, then this is B, Boolean product A, and we have two completely different matrices. And I should also specify that this is a non-commutative semi-ring when n is strictly greater than 1. Because when n equals 1, we have that it's isomorphic just to the set itself. So this, I think, gives a very good number of examples, right, showing in general what we can do with rings and why rings are so important. And what I'll do is just kind of lastly finish this lecture with the definition of a field. And using the previous definitions, a field F is a set A with two binary operations. Star plus and star dot that we, same as define their functions from A cross A to A from the ring definition, such that A and star plus is an abelian group, or we have associativity, we have an identity element with respect to this operation, we have that the existence of an inverse with respect to this operation for any element, and lastly, because it's abelian, we have commutativity. And we'll call it E the identity, the additive identity. So the second thing that we have to have is that A star dot minus the additive identity is an abelian group as well. So we have to take out the identity. Namely that multiplication is associative, multiplication has an identity element, and multiplication has an inverse for every non-identity element or non-zero element in the set itself. Then we can find an alternative element such that the element A multiplied by the inverse element is equal to the multiplicative identity from this group right here. And lastly, because it's abelian, it has to be commutative under this multiplication. And then the last thing that we have to have is distributivity. Of star dot with respect to star plus. And for some examples, we have that rational numbers with normal rational addition and multiplication is a field. The real numbers with normal addition and multiplication is a field. And the complex numbers with normal addition and multiplication are a field. A non-example, the set of integers with addition and multiplication is not a field, namely because the integers minus 0 under multiplication don't have inverses. So for any non-1 integer, right, there exists no multiplicative inverse of that integer. This is not an example of a field, but of a ring. Each one of these fields are also ringed. And for a very important example relevant to what we're talking about right now, modular set of modular numbers with modular addition and modular multiplication is not generally a field, because of the lack of inverses. I mentioned this in a previous example. But it will be a field, and we'll end up proving this. If M is prime. Which will be proven. But this is the conclusion of this lecture. I hope that it's been illustrative for you and you definitely learned something. And I hope you had a fantastic day.